Hello and welcome guys to yet another video, and actually this is not going to be just a single video, it's going to be a video series or an entire course. So if you watch the intro, you're probably thinking exactly what I'm thinking, or I should say I'm not thinking about anything because I've been working on this for about 2 months. So if you missed me, welcome back. I am back, and I am back for a while because this is going to be quite a lengthy course. It's going to be a course baked with so many examples, with so many things, and I am just scratching the surface in the first video. And if you don't trust me, you're gonna check out the resources and you will see for yourself. And now for those who are new to this channel, if you're new to this channel, make sure to hit that like button, hit that subscribe button to not miss any kind of videos, especially the videos from this upcoming course. And also make sure to share this video and also like if you find any value by the end of this video or any kind of video you're watching on this channel. That's why I want to stress out that this course may not be perfect for everyone because I will not cover the basics like if statements, for loops, variables, constants, types, structs, all that kind of stuff. So as you all know, I give access to pretty much everything on GitHub, and this course is not an exception. In fact, let's open up github.com/golang basics/concurrency, and on this specific URL you will find everything related to this entire course. And as you see, we have a lot of examples here, a lot of stuff. Yeah, pull requests are more than welcome. I will accept them. So yeah, feel free to check it out by yourself. And without too much further ado, let's dive into this course. Now, I know it's a lot of talk, but I have to stress this out so that you guys are aware of what exactly we're gonna do, what's the roadmap, what's the plan for this entire course. This is why let's go through the overview of this course so that you guys know what to expect, you know what to follow along. So in the first lecture, or in the first couple of lessons, we're gonna touch on concurrency theory concepts, concurrency basics, and basic introduction to concurrency and how that is done in Go. We'll then dive through concurrency primitives, the primitives which Go provides in its own standard library. After that, we're gonna follow along with Go routines, then channels, after which we're gonna dive into advanced techniques on how to use Go routines and channels in conjunction. Then the thing which a lot of you are probably here for, we're gonna dive through concurrency patterns, and I've baked a lot of patterns for you. As a matter of fact, you can check out the patterns folder in the GitHub repo. And at the end of this course, we're gonna dive through the Go scheduler and the behind the scenes, what exactly is happening in the runtime in the Go programming language, how exactly things are getting scheduled and all that stuff. Along with that, we're also gonna tackle testing, benchmarking, tracing, profiling, and all these tools which are very beneficial and useful when it comes to writing concurrent programs. And of course, alongside each topic that I'll cover, I'll provide mini projects, mini examples, which will be very helpful along the way. But of course, I'm not going to limit myself to mini projects. At the end of it, we're gonna build a bigger project which implements pretty much all of these concepts that I'm gonna teach you in this course. And specifically, we're gonna implement an AWS S3 bucket clone, which sounds like a simple project, but you will see it's a very complex project which makes use of all these concepts that you will learn by the end of this course. What exactly you'll be getting by the end of this video is we will learn about concurrency basics, concurrency theory. We will explore a couple of examples, and of course, let's not waste a lot of time and let's dive into it. Now, speaking of our lesson, I said we're mostly going to cover concurrency basics and what exactly is concurrency, introduction to concurrency, and all that stuff. So because of that, I want to begin with the resources that we have inside our machines. I want to begin with the CPU. So when it comes to the CPU does a lot of things on its own, but it doesn't do everything on its own. So in a concurrent world, you will be limited by the CPU resources, but you will also be limited by how much RAM you have and how much disk space or storage you got. And then imagine you have your Go application or applications sitting on a specific operating system. Now, in order for your Go application or applications to interact with all these resources, the CPU, the storage, and the RAM, you have to go through the operating system. Specifically, you have to go through something called the OS kernel, which is that thing responsible for communication between processes and the operating system. So when it comes to the CPU, as you all already know, and even when you buy your computer, you're looking for such benchmarks, is the number of cores it has. So in my case, I have an i9 Intel CPU, which means it has 8 physical cores. And if you have something like hyperthreading turned on, it means your physical core will become multiple logical cores. 8 physical cores, it's going to be 16 logical cores. So now that you know all this information about CPUs, physical cores, logical cores, which I'm sure most of you already knew, I had to make sure that everyone is on the same page. But now that you are all on the same page, we can proceed with other kinds of resources which your machines have specifically when it comes to the CPU. Before we do that, however, let's jump into a terminal and run a couple of commands in order to inspect a couple of things that our CPUs offer. So the first command I want to run is sysctl. So let's say sysctl, and let's run something like HW, which I believe stands for hardware, .logical CPU. So let's say logical CPU. And as you can see, it gives us back 16. And if you're interested in knowing how many physical cores you have, it's simple. All you have to do is, instead of logical, say physical CPU, and it's going to give you 8, which is the number of physical cores your CPU has. And as a matter of fact, one of the things that Go is going to do before even getting to run your program is going to inspect the CPU for how many logical cores it got, and it's going to take that number and use it for its own ways of scheduling, which, as I said before, we will dive into later on. But because we started talking about the CPU, I also wanted to talk a little bit about threads and what exactly they are. This is pretty much what a thread is. It's basically like a bag or box full of tasks. So we basically have tasks in there. Those tasks may be tasks which are allocated by your Go application. And suppose you have a certain amount of tasks. Basically, threads are there to help you kind of parallelize work or kind of execute work in parallel or concurrently. We'll check out what exactly is in parallel and concurrently a little bit later in this lesson. Now, one logical core can execute maximum 1 thread in parallel, which means if you have 2 logical cores, you can execute maximum 2 parallel threads at the same time. If you have any kind of tasks which are blocking in the thread, it means the whole thread is going to block and you will not be able to execute other tasks which are part of the same thread, which are part of the same box or list of tasks it has to execute. And also, speaking of threads, what exactly is their place in the operating system? As I said before, you have the operating system, and the operating system interacts with something which is called the kernel, which is basically like a middleman between the operating system and all kinds of services, resources, daemons, applications, including Go applications. So inside the kernel, you have 2 types of threads. You have user-level threads and you have kernel-specific threads. Now, when it comes to user-level threads, a specific user, in my case, steevehook, has a certain amount of threads allocated, and these threads can be allocated by applications, including our Go applications. And then you have kernel-specific threads, which are threads managed only by the kernel, and you basically don't have any kind of access to those threads. You can't influence them by any means. So as I said before, threads are pretty much a list of tasks, a thread of execution. This is why it's called a thread. We'll call it a list of tasks which has to be executed by some kind of CPU core. So let's say in our example, we have task 1, task 2, task 3, and task 4. Each of these tasks will take a certain amount of time in order to execute. Let's say 1 second, 0.2 seconds, 0 seconds, and 0.1 seconds. Then what would make sense for a logical core is to execute task number 3, then task number 4, then task number 2, then task number 1, because this is the right priority. This is what would make sense in order to not waste a lot of time, right? So this is kind of the way we think the CPU core has to execute. It has to somehow have some sort of logic which would reorder those tasks in order to execute as efficiently as possible. Which brings us to the next question. What is concurrency? And is concurrency parallelism? What is one and what is the other? And I'll tell you this, concurrency is dealing with a lot of things at the same time. Parallelism is doing a lot of things at the same time. Dealing with a lot of things at the same time / doing a lot of things at the same time. If you can't spot the difference, let me give you a simpler example. So again, let's think you have your good old CPU and you have a certain amount of tasks, let's say inside a thread, and you want to execute those tasks, but you don't know how much time each and every one of those tasks will take. Let's say the first task is going to take 1 second, the second is going to take 0.2, the third is going to take 0 second, and the last task will take 0.1 seconds. Now, how exactly the CPU will behave in this type of situation? Good question. So how pretty much the CPU will behave, it will have some kind of ticker. Let's say that ticker will execute every once in a while. Let's say once in a while is 5 milliseconds. So it will go for each task and try to execute for a certain amount of time. And that, if that certain amount of time passes 5 milliseconds, it will try to move on to a different task. And this is what's called context switching, which basically means if a task is taking too much, probably there's another task waiting, which takes less time, which I can execute and I can save some amount of of time. And this is what's called concurrency. When the CPU or the core has to deal with many things at the same time, it will try to execute one thing. If that thing takes a lot of time or that task takes a lot of time, it will try to move on to the next task. If the next task is executed successfully, it will try to come back perhaps, or will try to move on to a different task which is available, and so on and so forth till all the tasks are executed inside a thread. Now that was concurrency. Concurrency, which as I said before, is dealing with a lot of things at the same time. Now what is parallelism? So imagine instead of one core, you have two cores. And imagine you have exactly the same threads, exactly the same amount of tasks, task 1, task 2, task 3, and task 4. And let's say each individual task has its own burst time. And because we have multiple cores, we can execute things in parallel, which means we can do context switching in parallel, which means we can do concurrent things in parallel, which means we can deal with a lot of things in parallel, and we can check if one task is available, if one task takes longer than the other, if one takes shorter, lesser amount of time than the other. So the idea is very simple. Concurrency is dealing with a lot of things or a lot of tasks at the same time in the context of a CPU, and basically context switching between tasks until those tasks inside a thread are completed. Parallelism is pretty much taking the concurrency process and applying it on multiple cores, on multiple machines / multiple CPUs, and so on and so forth. You can scale your resources, but the idea is the same. It's going to use concurrency behind the scenes. Now we've talked about concurrency, parallelism, and how exactly that is happening on the CPU. Now let's get a little closer to Go and to our Go application and how exactly that happens in Go. So again, if you go back to our good old CPU, and this is pretty much how the picture looks from the operating system point of view. We have the CPU, the cores, and then we have the threads, and those threads have a certain amount of tasks to be executed. And the question is, where does Go fit in? That is very simple. You have your Go application, and that Go application is wrapped around something called the Go runtime. Basically, the Go runtime has everything that a binary needs in order to execute. So basically, it has the garbage collector, the scheduler, all the resources which Go will use in the end when it's going to execute that binary. So part of the Go runtime is also the Go scheduler. So basically, the Go scheduler's job is to do the heavy lifting when it comes to concurrency for you, when it comes to parallelism and all that stuff. It will basically create threads for you. It will execute or schedule those Go routines on specific threads. It will make sure those threads have distributed amount of work equally and all that stuff. So basically, this is the job of the Go scheduler. And the Go scheduler, of course, interacts with the OS kernel, because everything that has to do or has to deal with your machine resources, things like CPU, storage, RAM, and all that stuff, it has to go through the OS kernel. All right, so now that we had a look at how exactly things get scheduled, how Go routines get scheduled by the Go scheduler, let's have a look at a couple of Go examples. Speaking of examples, let's go ahead and run a simple synchronous example without any kind of Go routines and all that stuff. So on my desktop, I created a directory called Concurrency, and inside this directory, I'm gonna put all the examples and provide you as a zip archive at the end of this video. And I created another directory for the synchronous tasks. So let's go ahead and create a file main.go. Let's say main.go, and inside of this, let's give it a package main. Let's say func main. Like in our diagrams before, let's create 4 tasks, and these tasks will be nothing else but functions. So let's go ahead and say func, let's say task 1, and let's duplicate this. Let's say 2 and 3 and 4, 2, 3, and 4. Let's say each individual task or function will take a certain amount of time to do their work. After that, they will exit. So let's go ahead here and say time sleep. Let's say, for example, 100 milliseconds. And after that, let's print something like task 1. And let's do the same exact thing for task 2, task 3, and task 4. Here, let's add, for example, 200 milliseconds to make it a little bit more dynamic. Here, let's say the task executes immediately. And here, let's also sleep for 100 milliseconds. Let's also change the names of the tasks. So let's say this one's going to print task 2, this one will print task 3, and this one will print task 4. And now let's go ahead and execute these tasks in the main function. And let's try and measure the time it's going to take in order to execute all of these tasks. So to measure the time, let's go ahead and capture the time.now. So we're going to say now, and we're going to capture time.now. And at the end of it, we're going to print something like elapsed, and let's say time since, which will basically measure the time it took us to execute all of these tasks, and we're going to provide now. So let's go ahead and execute all of these tasks and measure how much time it takes to execute tasks synchronously. So let's say task 1, 3 and 4, 2, 3 and 4. So as you can see, because we have time.sleep inside each and every one of these tasks, it will take us pretty much the amount of total times this one is going to wait on task 1, task 3 is going to wait on task 2, and so on and so forth. Now let's compare this exact example with an example which uses asynchronous code simply by adding that Go keyword in front. So I'm going to go ahead and copy this directory, paste it here, and let's call this one async-tasks. And I'm going to provide the Go keyword in front of each and every one of these tasks. And now let's go ahead and execute this function or this program. And as you can see, it takes 9.336 nanoseconds, which is not the real example. And also, as you can see, it only printed task 3 when in fact it was supposed to print all of them, right? If you run it again, as you can see, nothing gets printed. And why exactly is this non-deterministic behavior happening? So a temporary solution is adding a time.sleep, you may think, right? Well, let's go ahead and add a time.sleep here. So let's say after task 4, we add a time.sleep, and let's say we sleep for a second, right? Let's go ahead and execute this example, and as you can see, it pretty much executes or prints all of these tasks, and it also says it elapsed in 1 second. Now, as you can see, we did fix the situation when the main function did not wait for goroutines to finish. However, the elapsed time right now is 1 second, which is exactly how much we sleep. And this is not correct. This is not what we want. So to solve this situation, you have to understand something called the fork join model, which is the way Go handles concurrency. So let me explain you a little bit what is the fork join model, and then we'll come back and fix this example. As you saw in the example before, you may ask yourself what exactly is happening and why exactly our main function is not waiting for goroutines to execute. We're spinning a couple of goroutines, and supposedly the main function is supposed to wait for them till they finish, then exit. However, the main function is going to exit right away. And why exactly is that happening, you may ask yourself? Well, first of all, the main function from the main package, when executed, it's going to run in its own Go routine, which is called the main Go routine. Another thing you have to know about concurrency in Go and the way it's done in Go is the fact that it's using a fork join model. So in a fork join model, you have the main function, and the main function has a couple of tasks, and at a certain point in time, you have the Go keyword, which means it's going to tell the scheduler to go ahead and schedule that Go routine. So basically, this is what's called a fork, which means from this point in time, this specific process is go in its separate way. Now that child process has its own list of tasks and so on and so forth, but after a certain amount of time, or after the child process has finished its list of tasks, its amount of tasks, it has to do the join. It has to go back into the main process, which is basically called a join point. If it doesn't go back into the main process, or if the main process does not expect a join back from that fork which was done initially, basically the main function is going to say, oh, we're done here, we don't have anything to wait for, we're done executing all the tasks in the run queue, so we're basically going to exit. And this is exactly what's happening. All right, so now that you know what exactly is the fork join model, let's go ahead and play with a couple of examples to see what exactly is that and how exactly that works for our Go application. So I'm going to create another directory called fork join, where I'm going to store all of these examples. So let's say fork join, and I'm going to store all the examples here. So let's first of all create an example which proves that adding a no join point will actually make the main function, the main Go routine, exit right away, thinking it doesn't have any more tasks to execute. And inside this directory, let's create another directory called, let's say, no join point. Now let me prove you that. Let's create another file called main.go, as usual. Let's give it a package main, func main. So let's go ahead and create a function, which will after that get executed using the Go keyword. So let's say func work. Let's again sleep a couple of milliseconds. Let's say time sleep. Let's say we sleep 500 milliseconds. And let's print, for example, let's say font, print line, let's say printing some stuff. So let's first of all call the work function concurrently by using the Go keyword, of course. So let's say go work. At this point in time, we created a fork. We created a fork point, right? So we have a fork point right here. Now we have to create a join point at some point in time. So let's say the main function also has some work to do, but that work takes a little bit less time. Let's say time.sleep, let's say 100 time millisecond. And then let's say, for example, font print line, let's say done waiting, main exits. Right here should be our join point. So basically our join point here is missing, and if we try to execute this function, nothing will get printed except done waiting main exit. So let's run this example. As you can see, it says done waiting main exit because it doesn't wait for this function to run, and it thinks it's done executing all the things, and thus it exits. Now we said that we had a missing join point. How the hell we create that join point? Well, that join point is created using something like wait groups or channels. So again, don't worry about wait groups or channels. We're going to cover those in details. Right now, I just want to demonstrate how fork join model works. So let's create another two directories, one for let's say wait group join point, and let's create another one for channel join point. So let's start first with the wait group, and let's create a function called main, and as usual func main. And as a matter of fact, I'm going to go ahead and copy the exact same example which had no join point. So I'm going to go here, copy this, and let's place it in here. So we have a fork point right here, right? Now let's go ahead and create a join point which will make the main function wait for that goroutine to execute before it actually exits. So let's create a wait group which is provided inside the sync package. So let's say var wait group, let's say sync.wait group. Now that we have a wait group, we have to call a function called add, which is basically going to tell the wait group, this is how many operations you have to be waiting for. Wait group add, we're going to say 1 because we basically just execute only one goroutine, so we want to wait for one goroutine. So on wait group, there's also a function called wait. So wait is going to basically be our join point. So I'm going to say wait group.wait right here where it says join point. When it comes to our fork point, instead of calling this work function, let me actually go ahead and call an anonymous function and run that using the Go keyword. So I will say something like this. This is a very common practice when it comes to concurrency and running Go routines. And I'm going to run this work function inside an anonymous Go routine. And now let's go ahead and call wait group.done, which will basically tell our Go routine that we are done executing work. We're done here. You can go ahead and exit now. So I'm going to go inside this anonymous function and say wait group.done. I'm going to add a defer statement in front so that this executes before the Go routine exits. I will go ahead and remove this time sleep because we no longer need this. And let's move this statement after the wait statement. And this is pretty much it. So I'm going to run this example. And as you can see, it's going to wait a little bit. And then it's going to say printing some stuff, which comes in from the work function, and then say done waiting main exit. And in fact, why don't we just measure the time? So let's come here and say now. Let's say time.now. And then at the end of this, let's print something like elapsed. And let's print time.since, and let's print, or let's use that now. And if you try to execute this again, as you can see, it says elapsed about 500 milliseconds, which is exactly how much time this work function waits, or the simulated work is waiting. So I'm going to copy the exact same example to not waste a lot of time. I'm going to copy the example with the wait groups and paste it inside the channel join point directory. So everything stays exactly the same, except we're going to replace this with channels. So I'm going to go ahead and actually remove this declaration, remove this wait. So I'm going to create a channel. Let's say done. Let's say make, which is going to make a channel. And let's say chan of struct. Let's remove this call to defer, and let's say something like this. After we call work, let's go ahead and say done, and we're gonna write something like this. And before we say elapsed, let's go ahead and say something like this. And this, as I said before, is nothing else but a join point. Here, when we say go and we run this anonymous function, we basically create a fork point, and here where we wait for somebody to write to this channel, we create a join point. So let's go ahead and run this example. As you can see, nothing has changed except we replaced wait groups with channels. So let's go ahead and run this example, and as you can see, it pretty much prints and runs exactly the same. It also takes about 500 milliseconds, and this is how the fork join model works in Go. This is pretty much what we will be using throughout this entire course. You'll be using a lot of fork join model without even thinking about it or thinking that it's called this way. Now let's go back to our async example, which, as you remember, we just sleep 1 second and the elapsed time is not printed correctly, and fix that using some kind of join point. We're going to use a channel join point. So let's go ahead and open up async main.go. And instead of sleeping here, we're going to do exactly the same like in the previous example. Let's say done. So I'm going to say done. I'm going to say done. I'm going to say done and done, for example. And let's say done is a chain of struct, and also done is a chain of struct here and here and here. And then after we wait, we print, we call done using the exact same construct. We basically push this value here, 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 and here. And what else needs to be done is to actually make sure we read the value 4 times. So we could say like this, we could do it like this. This is pretty much what we need to do. So if you run this example, as you can see, we're going to wait for all the tasks to execute. And as you can see, it takes much less time. It takes 200 milliseconds as opposed to about 400 milliseconds in the example using the sync. Concurrency can get quite messy. And here are a couple of issues. Here are a couple of problems which concurrent code usually faces. One of them is race conditions, is when multiple pieces of concurrent code try to access some kind of shared data. Then you have deadlocks when processes wait for one another forever, which causes a deadlock. Then you have live locks when processes pretend they're modifying a common or shared state. Then you have starvation when a process is trying to kind of violate CPU for longer than other processes. And lastly, you have code complexity. Writing code which is concurrently or which execute concurrently introduces a lot of complexity. And don't worry about all these issues. Don't worry about all these problems. We're gonna cover all of these later on in later lessons. Before wrapping this video up, make sure to check out that GitHub repo where I linked everything when it comes to presentation notes, coding examples, and everything we used in this specific lesson, and everything we will be using throughout this entire course. I know it was probably boring for many of you, but we had to dive into these details. We had to cover these basics so that everyone is on the same page with us. And yet again, guys, if you found any value during this time of this video, make sure to hit that like button, share this video, and also subscribe to this channel if you aren't part of this community already. And speaking of the community, make sure to join our Discord server and check out the description of this video where you will find the link to the Discord community. And finally, if you guys believe in this work, if you guys think I deserve your support, I created a Patreon page. Make sure to go ahead and support me there if you feel like so. And lastly, if you are as hyped and as excited as I am, I'll see you guys in the next video. Peace!